by Oliver Schlotterer from München. He'll talk about polylogarithms, multiple zeta values, and superstring amplitudes.
Thanks a lot to Herbert and the other organizers. It's a great pleasure to be invited to this workshop. I'm really grateful to the mathematicians for their interest in interacting with physicists. Yeah, like Stefan Stieberger, my former PhD advisor, I'm working on superstring theory. And we are seeing a lot of interesting mathematics and about multiple zeta values and many other things in our amplitudes, which we're always happy to discuss with the experts. It's really a great pleasure to have this opportunity for cross-fertilizing with you. So this talk is something like an analytic continuation to the talk by Stefan Stieberger in the morning. I will briefly review the problem which he presented, and I will mostly show you the toolkit, how we actually perform these alpha prime expansions, which lead to the beautiful results that Stefan presented in the morning. And as you see from the title, polylogarithms will play a key role. I'll introduce them later on. And for the beginning, I'll try to come back to the physics problem a little bit to give you a little idea of what the connection to the universe and everything is of the multiple zeta values we see. Okay, so I'll mostly discuss the interaction of open string states. And we'll do any number n of these guys at the same time. These states, yeah, they are just labeled 1, 2, up to n. And now, what is the geometric picture behind a superstring interaction? If you believe that the universe is made of one-dimensional strings rather than point particles, then a typical interaction process might look like this, where you have some string states, some string vibrations coming from infinity, which meet somewhere in space-time. And since the strings by themselves are one-dimensional, their propagation in space-time will lead to a two-dimensional surface. This is what we call the world sheet. So here I'm drawing a world sheet for you, where 4 open string states split or join or interact. And now you can classify these interactions according to the genus of the world sheet. In physics terminology, this is the so-called perturbative expansion. For each genus of a world sheet, we have a separate contribution, and it's something like an expansion and recoupling. But for the moment, we'll stay at genus 0. I'll discuss the leading contribution of the recoupling expansion for such an open string interaction. So here, we're discussing the disk. If it's about open string states, then the genus 0 topology is the disk. Okay, we are trying to attach open string states to a Riemann surface of genus 0. And now the mathematics that kicks in. To describe superstring interactions, what you have to solve is a QFT on the world sheet, a two-dimensional quantum field theory which enjoys conformal symmetry. And this conformal symmetry allows you to make exact statements, to solve these correlators exactly, at least genus by genus. So here, the information about the open string tree-level scattering is sitting in a CFT correlator on the disk. Okay. Now, these open string states, they're essentially states which are also treated in point particle framework. These are the gauge bosons of Young-Mills field theories. So there must be some connection between the stringy picture with a world sheet and the point particle physics, which is conventionally described in terms of Feynman diagrams. So as a subset of this string amplitude, we have the typical Feynman diagrams, which you know from physics of the standard model, well explored for decades. And there are several Feynman diagrams which are capable of describing such a 4-point interaction. And as a first advertising statement about string theory, it captures a cornucopia of different Feynman diagrams with a single world sheet diagram. It's much less bookkeeping than in field theory. However, string theory is more than just a field theory. These Feynman diagrams are decorated by some stringy effects. And this stringiness enters in the form of Selberg integrals. which Stefan has shown to you in the morning already. Okay, to make this qualitative statement a bit more precise, let me write down our mathematical objects here. Such a worldsheet represents a scattering amplitude. A scattering amplitude where I have to specify the cyclic order of the labels. Remember, we're talking about a disk topology, and there are several cyclically inequivalent ways how I can place my scattering states on the boundary of the disk. So here I have to specify the cyclic ordering, and it's sufficient to just consider a subset of cyclic orderings where n minus 3 legs are permuted in any way possible, and it's always possible to keep 3 of them fixed. So here in these n minus 3 factorial permutations, I'm carrying the complete information on the superstring disk amplitude. And now the opening line of Stefan's talk was that this string amplitude expands into a sum of field theory objects. Namely, all the state dependence is sitting in the analogous subamplitudes of Young-Mills field theory. So here this subscript ym is telling you that here I'm writing down an object from point particle theory. And this object, A Young-Mills, subject to a cyclic ordering, this gathers many of these Feynman diagrams.
But they're all trivial because none of them have loops.
Oh yeah, all of this is tree level both on the Young-Mills side and on the string side. Okay.
So
oh yeah, essentially I'm giving you 2 different permutations on the left and on the right, and now the stringy physics enters through a matrix which rotates the different Young-Mills permutations into an individual string permutation. So you're taking the next object ahead, which I have to write down here. Each of these field theory subamplitudes is decorated by a different Selberg integral. So here I'm writing down n minus 3 factorial by n minus 3 factorial matrix of Selberg integrals. Yeah, as I said, they simply rotate the vector of field theory amplitudes into the string theory quantity you're after. Yes, please?
Selberg integrals is a CFT correlators, right?
They are the result of the CFT correlator, exactly. And let me stress the
Alpha prime is some coupling constant.
alpha prime. You can think of alpha prime as being the square of some fundamental string length scale. Yeah, that's
but the only connection to field theory is that alpha prime equals 0.
precisely. At alpha prime equals 0, this has to become the identity matrix. Right. Yeah, so what's nice about the result is a separation. The stringy physics is sitting in that guy,
Yeah.
whereas all the state dependence is
So
sitting in the field theory building blocks.
So everything with alpha prime greater than 0 has no relation to experiment.
So far, at least. Let's hope that alpha prime is large enough that we can sooner or later measure it, but this is a separate story on its own right. Okay. Yeah, so all the alpha prime dependence, as I said, is sitting in this Selberg integral matrix F. And it enters implicitly through the so-called Mandelstam invariants. And I define my Mandelstam invariants Sij such that they are dimensionless. It's exactly the same convention which Stefan has used in the morning. And these K, these are simply the external momenta. Since alpha prime has units of square meters, then combining it with 2 momenta makes it dimensionless, at least in some natural units for physics purposes. All right, so if I'm talking about an alpha prime expansion of these guys, then in fact I'm talking about a simultaneous expansion in all the Sij at the same time. Now I have to give you the integral representation of these F pi sigma. On the disk, you can make use of conformal symmetry to fix 3 positions to any value you like. So the true dynamics is only restricted to n minus 3 integrations. So these Selberg integrals, they involve n minus 3 integration processes. And now I'm giving you the integrand, which is the result of the CFT calculation. First of all, there is this ubiquitous factor, we call it the Koba-Nielsen factor, where all the differences enter with the modulus and the power of the Mandelstams. Excuse me, Don?
Just for notation for mathematics, product doesn't mean what we mean by product. You're not multiplying these integrals. You mean you're writing what we would write integral dot 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 integral. It's not a product.
Okay, it's probably a sloppy way of saying what you spotted. It's integrating over Z2, Z3, Z4.
So it's not a product. I mean, this is really confusing for a mathematician. If you write
I
product,
apologize.
then you expect the thing afterwards to factor, but it's not. You just mean
Okay.
integral dot 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 integrals. You're multiplying
Indeed.
Leibniz's S with itself, but it's just a symbol. Anyway.
Okay, yeah, I'm using the integral symbol here. What I want to say is that we integrate over all the variables C2.
Yeah, at least if you put the integral and then product of the DCs, everyone could understand.
Yeah.
But you've written
Oh,
product of integrals.
it's that easy.
It's that easy, yeah.
And they would understand that.
We would still prefer the DCs on the right, but this at least makes sense. The other doesn't make any sense at all.
Okay.
Yeah.
There's a difference between product of integrals and integral of product, as you well know. So it would be much easier.
All right. Thank you. So I hope that the remainder of my products and sums in this talk are more accurate. First of all, there's the ubiquitous Covariance factor, which is no surprise to appear. And now the, let's say, less trivial part of the CFT correlator. It's a telescoping product of sums, where you get various combinations of Mandelstam variables, which are always paired with the differences of positions Z. So in the worldsheet picture, you can think of all these Z's as being the complex coordinate that parameterizes the worldsheet. As Stefan has told you, you can nicely map the interior of the disk to the upper half plane, and open string states are inserted on the boundary. So in the upper half plane picture, the disk boundary simply becomes the real axis. So all these Z's are somewhere located on the real axis. And now I have to take the ordering of the external states into account. Since I'm specifying an ordering of points on the disk boundary, I should make sure that the integration domain respects all these inequalities. Okay, so thinking of F as a matrix, the pi index is making reference to the integration domain. This is the only place where you see a pi on the right-hand side. And the other index, sigma, is making reference to the particular integrand, to the particular differential form which you're integrating.
So they're also between 0 and 1? Where are they running disease?
Okay, the next thing I have to tell you is what happens to the positions I have fixed by virtue of conformal invariance. I have fixed Z1 equal to 0. And I have fixed Cn minus 1 equal to 1. And finally, Cn is at infinity. And because of this choice, the covariance factor only runs to n minus 1, since the poor guy at infinity doesn't really interact. Okay, so this is the period matrix which captures all the alpha prime physics in the superstring tree amplitude. Now, as Stefan has told you, there are multiple zeta values in the alpha prime expansion of these guys. Multi-zetas in f of alpha prime. And in order to understand the systematics of the multi-zetas appearing therein, it's preferable to map to another.
Sorry, no, don't go so far. I mean, I know we saw this morning, but does this mean that f pi sigma only depends on pi sigma inverse?
Yeah, that's right. That's right.
If you call z
yes?
sub pi of I, just call it x sub I, then you have 0 less than x1 less than x something less than 1, which doesn't tell anything. And the integrand is always the same. Everything's the same, except that Sij is now s sigma of I comma sigma of j.
For sure.
So pi of I. So it only depends on.
There's some redundancy. There's just.
Well, no, it's diagonal. I mean, it only depends on.
It just depends on
there
the.
are only n minus 3 factorial entries that are different, and then they repeat. Not the square of that. I mean, it just depends.
Maybe it's fair to call it there n minus 3 factorial functional dependencies. Would you agree with this wording? Yeah. So there's a lot of redundancy. If I just know the first line.
This matrix has the form A on the diagonal, B on the next.
But the diagonal elements, they are related to each other by the permutation. So you have to simultaneously permute all the labels 2, 3, 4 up to n minus 2. But you're right to point out there's some redundancy there.
I don't understand. There is no permutation.
Sorry?
The permutation is the position on the matrix.
just maybe.
Let's say n minus 3 were 6, then you've got a 6 by 6 matrix.
Yeah,
In which the
let's
6
even
diagonals will all be the same.
Let's even go back to the 2 by 2 case. Stefan has shown you that the F matrix at n equal 5 is given like this, where those guys are related by swapping 2 and 3. And at the same time, these guys are related like that.
It only depends on alpha prime.
It depends on all the Mandelstam variables. So you have to perform some swappings like this one. Or maybe it's
just
helpful.
didn't write that. So it's a function of the S's, not the alpha prime.
Yeah, so as I pointed out, in fact, this alpha prime represents all the S at the same time. Yes. Okay. If you prefer, we can put
alpha prime, not
we can put the argument like this.
Okay, that
Is it better this way?
yes, that then I wouldn't.
Okay.
Could I ask a question? So these integrals have a dihedral symmetry, and you've only taken a cyclic symmetry. Does that give this what you've written on the matrix here, F1 to F1 tilde? Is it precisely this fact that the cyclic is subgroup is of order index 2? And
Okay. You mean so you're
many
suggesting that
vectors have
dihedral symmetry is responsible for the fact that we only have n minus 3 factorial different functional dependencies?
You don't see the dihedral symmetry in this integral.
well, you start off with the cyclic symmetry, and then the integral has a dihedral group acting on it that preserves the domain of integration. So I was wondering, you've got an extra involution somewhere. Is that what you wrote on your matrix? F1 goes to F1 tilde.
Okay. Difficulties to answer here on the spot. So can I leave you for the moment with a
I'll
statement?
keep it there.
Knowing the first line, you know all the rest. And in fact, the remainder of the talk will be about the first line. So indeed, there's no need to worry about this. Okay. So where did we stop? Yeah, I was about to tell you that, I was about to repeat the key information of Stefan, that the multi-zeta content of this matrix takes the nicest form if you map all the multi-zetas to a certain Hopf algebra co-module. You get a particularly nice pattern under the following map. First of all, you naively get multi-zetas if you perform this expansion here. Now the first step is uplift all these guys to their motivic version, and then make use of the Hopf algebra structure, which, among other things, allows you to map any multi-zeta to a co-module which is generated by objects F3, F5, and so on. Strictly speaking, I have one co-generator for each odd number, 3, 5, and so on, and you consider all non-commutative polynomials in these co-generators. And on top of that, you need to adjoin an extra commutative element called F2. This, by definition, commutes with all the non-commutative co-generators. And you can already anticipate that this F2 object takes care of the even single zeta sectors, of all the even single zetas which are related to powers of pi by rational numbers. Okay, so under this isomorphism phi, the superstring amplitude becomes particularly nice. Phi, acting on the motivic version of this period matrix F, as shown by Stefan, takes the following form. There's a matrix multiplicative pattern where on the left you can some sort of factor out all the F2 dependence. So here, that's, if you wish, the even zeta sector in terms of the commutative variable F2. Now I have to tell you what P is. I'm using matrices PW and in a second MW, which are just like F itself, n minus 3 factorial by n minus 3 factorial. And the subscript here is giving their homogeneity degree in all the Mandelstam variables. And according to the definition above, this is the alpha prime order. Okay, so here are the even matrices P, and now they act by left multiplication on all the odd matrices or the odd sector, enters through a sum over all non-commutative words. We take all possible compositions of f's, of f odds to be more precise, and now their coefficient is a matrix product. Matrix product made of these m's, which appears in the reverse order. So if you form the word in f's like this, then the matrix multiplication order just goes in the opposite way. So here these arrows with some quotation marks, just to highlight the structure. Okay, so the subscripts here are running over the odd integers larger than 2. Good. And as you see in this formula, these P, W, M, W, these are the independent building blocks, and they are, by definition, the primitive coefficients of the period matrix F. Okay, so here this is a very economic form to organize the multi-zeta expansion, since you only need to know the primitive coefficients, P, W, M, W, as independent information, and all the remaining multi-zeta coefficients are then fixed by this matrix multiplicative pattern. That's a nice property of this formula. Okay, so far there has been nothing
You haven't
new.
know the P's and yet.
Yeah, so far we haven't said anything about what the
But
P's and M's
but
are.
you're saying this reduces everything to knowing one M for every odd index and one P for every even.
Exactly.
But you haven't told us anything that reduces it. I wasn't sure if you'd said one of them follows from the other. You need
No,
both.
not at all. Not at all. So the remainder of my talk is devoted to the challenge of computing them in ideally in full generality for any number of external states and as high as possible in weights. So the main point of my talk is to introduce a machinery to carry out these multi-zeta expansions efficiently. I want to address the question how to alpha prime expand the period matrix F, and essentially this question reduces to the computation of all the PWs or MWs. How can we perform this? This will be the topic for the remainder of my talk. Any questions about the general setup? Okay, now let us go into more detail. I've given you the full integrand of the f's, and essentially this part here of the integrand boils down to rational functions of degree minus n plus 2 in the set differences. So write down the most general thing I have to expand in the following. We want to expand integrals labeled by n minus 3 minus a, which I define as follows. Now I have to pay attention to the order of the integral sign in the product. It makes sense to reshuffle these rational functions towards the dz, just to read off the differential forms in the game. And the integration domain, well, in the end, it's sufficient to just compute one disordering, since all the others will follow by relabeling. I think this is related to the conversation which Don brought up before.
Yeah, that was my question.
Okay, so for the moment, I'm just restricting my attention to the identity permutation, 1 to 3 up to n. So the integration domain for zk is given like that. And now I fear I'm running into slight inconsistencies now that I've permuted the integration sign to the left. So what this notation intends to say is just make sure that ci is smaller than ci plus 1.
That's right.
That's right.
Just write the integral dot integral and under it put just on the z.
Okay.
It's very easy. Notation is very easy.
So if you allow me, then I'll just carry on. Okay, so the object to expand, the elementary integral contained in these f's, is of that type where you integrate the Koba-Nielsen factor over n minus 3 differential forms. And for technical reasons, I should place the a's, these numbers here, such that they are either 0 or 1, or that they refer to a z whose subscript is larger. So it's a variable which is integrated over in a later step of the calculation. That's just a technical aside. But given this constraint here, there are n minus 2 factorial different integrands covered here. So this is for sure enough to expand any of these f's in the end, once you have solved this integral. Okay, so we are about to perform the Sij expansion of this integral here. And ideally, I would like to start this expansion on the level of the integrand. So ideally, I would just start expanding this guy, but there's one subtlety to take into account. Before I can do that, I must make sure that it's regular. And by itself, there can be problems about regularity, since the generic integral has poles in the Mandelstam variables. These poles, they stem from the integration region where neighboring positions collide. Okay, so before you can...
This form of integral, so it's an iterated integral. So you integrate
iterated integral.
You say that each ak is 0 or 1 of one of the zi's, and then you integrate out the i's
one after the other.
But you still say that the integral depends on i's.
So it doesn't make sense.
Okay, maybe it's more a labeling. It's more a labeling. It's just giving the names to make sure that.
So it's not this. So what you mean on the left is 1, 2, k plus 1 of n minus 2. These are labels.
These are labels. These are labels.
I mean, a might be fine. It wouldn't be 4 plus I.
Of course, you are free to
A
consider.
is not in the set of z's. It's in the set of labels. It's in the set that in your notation is 1, 2 up to 1, k plus 1 up to n minus 1. I think that's what you're saying.
Yeah.
They're integers.
Well, not necessarily. I mean, I want to be able to cover the case where you integrate that guy. So
yeah. So then
A2 is integrated like this.
So A2 would be 3. What you mean? Let me write it correctly. You really
Well, I would agree with you.
Oliver, just, yeah, exactly.
You would
Put here
prefer
Z sub A sub k, and remove A sub k, and put that A is in the set 1, 1, and then k plus 1 up to n
Oh,
minus 1.
that's my
And now it's
question.
correct, yes. I mean,
Okay.
it's really completely, you can't,
Okay.
it depends on the things you're integrating over.
Okay. Thanks for the notational advice.
No, you put n minus 1 at the end, and cross out the 1. Cross out the 0.
Okay, in that case, yeah, this has to be replaced like this, and this has to be replaced like that. You believe it's better?
I would have put it at the end, but that's fine. Yeah.
Yeah.
Okay. It's perfect now. We all understand.
Okay, very good to hear that. The message I want to bring at this point is that in general there are poles in these integrals, but luckily the residue of these poles has a recursive structure. Let's say it's particularly nice to see with some physics in the understanding in terms of Feynman diagrams, but I don't want to go into the details of this. Let us just keep in mind the residues are recursively determined by integrals with a smaller number of particles. So it's safe to say that if you firstly compute the endpoint amplitude, and you know already the lower point guys, then you have complete information on the residues. So there's nothing new happening in the residue. You can straightforwardly subtract them, and the details will be shown in the paper in progress. So I suggest that for the following, we assume that the poles have been taken care of. We assume that the poles have been subtracted. And for the rest of my talk, I would go ahead and tailor expand the covariance vector to extract the novel endpoint information on the alpha prime expansion. So once we have subtracted all these poles, the residual task is to tailor expand the integrand and to carry out the integrations order by order. So whenever you see such a difference, Ci minus Cj to the power of Mandelstam, you will replace it by this Taylor series. the residual task is to perform multiple iterated integrals over all kinds of logarithms of this kind here. And what is the right tool to perform this? This is the right time to introduce polylogarithms. The polylogarithm is defined in a recursive way. A polylogarithm with a bunch of labels, A1, A2, AW, and one argument, Z, is defined in terms of a small polylogarithm with one label less. It's defined in terms of a polylog where the first label is suppressed. And in order to append such a label, you have to integrate it over a differential form, which carries the information about this additional label.
Can you tell us where these things lie on the left before? So the argument is complex, real, the labels are integers, or they're just labels?
Okay, I believe they can be complex, but let's say for the purpose of today's talk, they are all real.
Oh, so they're not labels. These are variables. They're numbers. The variable is 1, 2, 3, 4. A label is 1, 2, 3, 4. X1 is a variable. I mean, this is a real number.
Okay, so
it's a function of simply many variables.
Yeah, it's a function of many
yeah,
variables where all the variables left on the semicolon enter on a different footing than the unique variable right of the semicolon.
Suggested from the semicolon. But anyway, they're just real variables.
And in abuse of terminology, I refer to all the guys left of the semicolon as labels, whereas I will call that single variable right of the semicolon the argument of the polylog. Okay, so here the recursive definition basically tells you can append an extra label by integrating a smaller polylog. And of course, this recursion has to start somewhere. The polylog with an empty set of labels is by definition 1, mostly, as long as the argument is not equal to 0. There's a subtlety about z equals 0, but you can safely say that an empty polylogarithm is mostly 1. Okay, why are these polylogarithms useful for our challenge of performing alpha prime expansions? We want to rediscover all the multi-zetas from the polylogarithms. And one key property of polylogs is they evaluate to multi-zetas if the argument z equals to 1. The precise relation is
multi-zetas are a countable set, and here you have an uncountable number. These are continuous variables.
Yeah.
Multi-zetas is a countable set, so this can only be true if you specialize everything.
Okay,
or
so
the Taylor expander.
The specializations appearing in this setup are all perfectly suitable to translate into multiple zeta values. Maybe this statement becomes more transparent if I write down the formula here. How you can represent any multi-zeta of depth r in terms of a polylogarithm at argument 1. And now the labels corresponding to a specific set of multi-zeta arguments is the following. It consists of many blocks of mostly zeros and one label 1. There's something like an inversion of order. So the rightmost argument of the multi-zeta appears on the leftmost end of the polylog labels.
Which is the rightmost?
The rightmost will be...
No, I mean, in the Zeta, there are two condensing. You didn't tell us which one you're using.
Okay.
In this whole conference, half the people do it one way and half the other. You haven't said which you can't do which is the one that has to be at least 2 to make it converge? Then one or another?
Sorry. Yes. This is the guy who should better be...
Okay.
Okay. Thanks.
You wouldn't have to reverse the order if you belong to the other camp.
if I belong to the other camp, yes. Absolutely. Okay, so to each of the arguments of the multi-zeta, I have a subsequence of labels which are mostly 0 and 1 times the 1. Up to here, up to the semicolon, it's about the labels, and finally the argument needs to be 1, such that the polylog evaluates to the multi-zeta. So this is how I want to extract the multi-zeta from the integrations which are contained here under this Taylor expansion.
E is 1 and every AI is 0 or 1, then the top statement is correct. It evaluates to multi-zeta if every A is a 0 or 1.
So in the intermediate step of the following, you will see that in the intermediate step you will have to struggle with labels that are not equal to 0 or 1.
But this statement
yes.
is obviously only right if the A's are 0 or 1.
Ah, okay.
That's all I know. Thank you.
Thank you. Right. Good. In order to carry this program out in practice, I should tell you two essential properties of the polylogs. Property number 1 is, how are they related to the logs, or to the power of logs, which I first of all get in the integrand expansion. If you take a polylog where all the labels are 0, where I have W labels 0, how can I relate it to logs? Well, first of all, I have to explain my funny notation here. Whenever I use an arrow with some real number below, then this can be thought of as a sequence of identical real numbers A. And this subscript W simply means that you take a sequence of length W, where all the members here are just the real number A. So in this notation, the polylog with zeros only in the label is related to a power of log set. And I can make similar statements if you have uniform labels, let's say 1. In case of uniform labels 1, and it's a slightly different log which you have to raise to that power. And finally, in the most general case of uniform labels, if it's any other real number A, and this polylog equals power of the log 1 minus c over 8, raised to the power 3. Good, that's key property number 1, which we will need at an earlier step of the calculation. And in addition to this, I should tell you about the shuffle algebra. What happens if you take a product of two such polylogs at the same argument? You can easily imagine, since there are plenty of such factors here, I have to make sure that I can squeeze products of polylogs to a single polylog. And the shuffle algebra does this job of putting a product together.
I mean, if any A, if A1 is 0, you have a problem of convergence. So
indeed, there are issues about convergence, yes.
So P is not defined the way you defined it. In the first line of this G of 0, 0, 0,
it's
with
absolutely
the infinite,
true.
of course.
I'm writing down formally divergent expressions, and everything I'm writing down shall be thought of as shuffle regularized.
Okay.
Okay. So, in case of a product, where the arguments are, sorry about this. I can boil down the product of a sum of individual polylogs, and in fact, I'm using a notation which is shown on another blackboard. What you have to do is shuffle the labels of the two factors. You have one polylog with labels A1 up to AR, and another one with a different word of labels, and then it evaluates to a polylog at the shuffle of the two words. So the meaning of this shuffle symbol, is explained in Exhibit 1, shuffle algebra. You see that this object here should be thought of as sum where I include those permutations in capital sigma which preserve the ordering within the individual words. So what the shuffle symbol does, it is as if you were playing cards and take two piles which you shuffle together. The ordering in the individual piles will be preserved, and the shuffle product tells you to sum over all possibilities how you can shuffle two piles of cards while maintaining the order of the individual stacks. Good. And to make a long story short, why I'm telling you about this shuffle algebra, it allows you to put together different polylogs in order to form one big polylog, such that you can later on integrate using that definition. Okay, let's make all of this a bit more tractable by discussing a toy example. As a toy example, I want to discuss the expansion of a 5-point integral, one of the integrals which appear in the 5-point amplitude. So in the end, you have to perform two different integrations. And I will choose an example which is free of poles straight away, just to avoid those subtleties. And to make the example even more easy, even more ridiculous, I will set one Mandelstam variable to 0. You will see later on why. Okay, well, the particular example I have in mind will be called I5 with A2 equal 1, A3 equal 0. This is essentially the integral with differential forms like this. I have to make sure that Z2 is smaller than Z3. And now I already expand the integrand. And as long as S to 3 is equals 0, I'm having 4 independent Taylor series. In total, there are 5 Mandelstam variables in a 5-point problem, and here I'm artificially setting 1 to 0 to make the first step of the problem digestible. Okay, so this is the fourfold expansion that remains. And for each of these Sij factors, I have one polylog, which emerges by property 1 over there. S12 is associated with a polylog at argument Z2, where all the labels are uniformly 0. And from the S2 form factors, you get that polylog. And already at this point, you probably smell that this is a thing to shuffle for later purposes. In order to proceed, we have to apply the shuffle algebra to this combination here. And there are 2 more Taylor series to consider. Associated with S13, there is polylog at argument C3, and a colleague with different labels. Okay, this is the thing to solve. Yeah. In order to apply the recursive definition of a polylog, you have to make sure that there's just one G and not a product like here. So at first you have to shuffle. By shuffling, you make sure that the result has a factor of this somewhere in its labels. Okay, once you have shuffled this here, then you are ready to perform the Z2 integration. This differential form here tells you that you have to append the 1. So after evaluating shuffle, you append the 1 to each of the sums according to the definition above. Good, now you are done with the Z2 integration, and since the upper limit is Z3, the result of this is a polylog at argument Z3. But it's not the only one. Apart from that guy here, you have 2 further polylogs at argument Z3. So what you have to do next is, once again, shuffle. Shuffle the result of Z2 integration into the remaining label vectors from the other two polylogs. Good. After this shuffling, you're ready to carry out the Z3 integration, and here that differential form here tells you to append a 0. And now you're really done with all this integration. The result is a polylog at argument given by 1. And this evaluates the multi-zetas. Okay, so this concludes the toy example. As long as you keep this particular Mandelstam variable at 0, it's just elementary integration. It's just the definition of polylogs together with their shuffle algebra, which gives you the alpha prime expansion. But now let's get a bit serious and drop the restriction to S23 equals 0. What if you keep it alive? Then you have to face a superficial complication. You then have to face powers of the logarithm where both the integration variables Z2 and Z3 enter. In order to include this extra factor into the game above, first of all you have to make sure to introduce it in the right form. The idea is to use the last property under 1. The idea is to use that property with Z2 over Z3 here. In order to bring it to that form, you have to factor out Z3. So what you get is a sum, just a binomial sum. Partly you have argument Z3 with label 0, and partly you have labels Z3, j of them, and argument Z2. Okay, now if we try to repeat the exercise from before, in presence of that factor, there's one problem. After Z2 integration, where this sign participates, you will have something like polylogarithm, where the labels are a word in 0, 1, and Z3. So this extra factor here increases your alphabet. All of a sudden you have a 3-letter alphabet where Z3 appears within your labels. However, Z3 is at the same time the argument. What you would like to do next is perform an elementary Z3 integration, but at this point you can no longer do that because of this clash that the integration variable Z3 is also contained in the label. You cannot integrate using star. I have to tell you what star is. You cannot rely on the recursive definition of the polylog anymore to carry out the Z3 integral. So at this point we have to rethink our strategy and develop a little bit more polylog machinery. Okay, here's the problem. You're faced with polylogs where the argument, the integration variable, occurs in the labels at the same time. And in order to solve it, we apply a family of polylog identities. Which schematically do the following. I claim that the following manipulation is always possible. Suppose you start with a polylog whose labels are from some alphabet, where one letter of the alphabet is the argument. Suppose you have this kind of clash, then my claim is it's always possible to re-express this guy in terms of simpler polylogs. By simpler I mean that you no longer have this Z in the alphabet, but you do this at the expense of introducing many, many terms. You will need plenty of such simpler polylogarithms, and moreover, the overall weight, which I denote by W here, will in general be split. Split among the simpler polylogs. Let's assign weight J to them. Maybe J is too much alike to the semicolon. Maybe K is a better letter. So I sum over all partitions of this weight W, where weight K goes into a polylog, and the remaining weight goes into multi-zetas. Identities of these kinds will solve the problem we are having here with particular integrals. Now let us look at some examples of this very schematic formula here. I hope I have some examples over there. Yes, indeed. In exhibit number 2, you see some examples of this technology. The first one has the C in the rightmost label. And this is a case where, as Don pointed out, shuffle regularization needs to be taken into account. Using shuffle regularization, I can re-express this polylog with a Z in its labels as a combination of simpler polylogs. The first terms on the right-hand side have the complete weight 3 in the polylog, but also the last term has weight 2 in multiple zeta, or here in the single zeta 2, and the remainder of the weight is sitting in a polylog of weight 1. And here you see a second example where I'm introducing more letters into the alphabet. And the upshot is that presence of additional letters different from Z do not spoil anything. Okay, so if you believe me that such identities always go through, then I can integrate every Taylor monomial. Let me just write down the most general Taylor monomial in the game. Now I'm trying to be accurate. The most general thing that remains to be done is evaluate this integral where some terms from the Kobayashi expansion are in the form of the toy example, namely for each integration variable Zj, we have some polylogs with labels 0 only, with some integers. So up to here, that resembles the toy example. But now that we have these extra identities, you can also include the superficially more difficult cases. You can also integrate if there are additional factors of the following form, where two integration variables, Ci and Cj, are combined in a single extra polylog. The variable with a larger label, Cj, in the label, and Zi, the argument. So now, given that extra technology, we can also take care of this admixture here. That motivates us to take these polylog identities serious, and in particular, this motivates us to prove this general claim that this reduction is possible. I'm now about to prove these polylog identities for you. Before I do so, are there any questions?
You have to define it before you prove it. I mean, if some z, if some a is equal to z, the integral is divergent. So you again have to regularize at both ends.
Yeah.
And in the integral defining the
Yes.
g by induction, you integrate up to z. So if z is equal to a, then you have a problem.
Indeed. So the usual problem of shuffle regularization.
Yeah, but you have to
persists.
you have to do two vectorizations at the 0 and at the z.
Precisely. Yeah.
You haven't talked about those. So. No, but the claim, all I'm saying is the claim undoubtedly can be made, does make sense to you, but as it stands, it doesn't yet make sense, and therefore can't yet be proved, I think.
So do you think I'm safe if I make the general disclaimer that all polylogs on the blackboard are understood to be shuffle regularized?
No, I don't say that. Well, it may be helpful. I mean, there are two endpoints. You have to do two
Precisely. Yeah. There
and
need
normal
to.
shuffle regularization, you only do one thing, but maybe.
Yeah, but it's always possible to let's say
do
first
it
regular.
but then you have to introduce two little extra parameters, epsilon and delta, that you integrate
Right.
not from 0 to z, but from epsilon to z minus delta.
Oh yeah. All this
And
goes.
then you have power series in both. So all of that's
Yeah, so
implicit.
you are pointing out a serious obstacle in our computer implementation of this.
Well, but
It
also
certainly
fine.
increases
No,
the.
but you want to prove this before you prove it. You should, which makes sense. But I think that's. if you, as long as you're sure as you.
But I'm curious to see at which part of the proof I have to pay particular attention. So I'm
I can tell you right now, one of the multiple zetas will be zeta of 1. Or will include zeta of 1. That when you know how to regularize. But you have to regularize the left hand side as well as the right hand side. You're proving inequality where both sides have infinite terms. You have to define them both.
Yes.
On the right, you've said that for the multi-zetas, you're doing it by shuffle regularization. You haven't told us what you do on the G. Of course, you do the same kind of thing.
yes.
I'm sure it's no problem. I'm just saying that it has to be done. I'm sure you've done it.
Yes.
Yeah.
But yeah, I can promise it was a big
I'm not-
source of complication, our computer implementation of this. I agree that it's a big issue, yes. Okay, so assuming that the regularization issues are settled, I will now proceed to prove the schematic claim on the other blackboard. For the moment, let us assume that there's just one instance of the unwanted integration variable in your label. For the moment, let's just say there's one instance like this. Okay, so I want to reduce some generic polylog with many labels AI, where at the ith position I have the argument z, which I want to eliminate in the end. And in order to eliminate, my opening line is a very elementary statement that function of z is the integral over its derivative. So let us look at the derivative of a function where these are simply replaced by t, an integration variable. Okay, now how does this total derivative from t act? Well, there are two places. There are two different partial derivatives which enter the total derivative here. And I have prepared some auxiliary identities in order to evaluate this. It's shown in exhibit number 3. Here are the identities if you take partial derivatives of a polylog. The first line concerns the partial derivative with respect to the argument. It's this arrow here. And from this, I get the following contribution. The partial derivative with respect to the argument simply gives you the differential form associated with the leftmost label A1. And then you have taken the A1 out of the word of labels. But you still have the T inside. Good. This comes from the first line. And now I have to look at the partial derivative with respect to that instance of t. This will give 4 terms in total using the exhibit above. So the identity goes on like this. I have a differential form t minus the left neighbor of the unwanted variable. I guess I should keep track of the term numbers. Here I've given numbers to the terms on the exhibit blackboard. This is number 1. This is number 2 here. And as you see, there's a hat above the AI-1 label. A hat means simply omitted. So here, term number 2 on that blackboard gives you a polylog where the vector of labels is shortened by omitting AI-1. Okay, and the same thing is done with the right neighbor instead of the left neighbor, including a relative sign. So also there's a term where you omit the right neighbor of the t variable. Good. This is term number 3. Okay. Now, terms number 4 and 5 are nicer for our present purposes because they are omitting the variable itself with respect to which I differentiate. Remember, our ultimate goal is to ban this integration variable from the labels. So terms 4 and 5 are precisely in the form like we like them to have. Term number 4 tells you to omit the t variable, or after integration it's a z. But the differential form, or let's say this rational function, 1 over ai-1 minus ai, this tells you to append the corresponding label. And the same thing happens for the right neighbor, ai plus 1. Again, it has the pleasant side effect of omitting the argument. Okay, this is term number 4, and this is finally term number 5. Now, what have we gained so far? The hope is that ultimately all the instances of t's are gone. And looking at the last 2 terms, I have perfectly accomplished this task. The last 2 terms are simpler than the left-hand side in the sense that there are no z's in the labels. So here we can make a big check mark. This is precisely what we want. But now, looking at the other 3 terms, they still have the argument within the labels. They still need the treatment which we were about to make. But there's one simplification. The string of labels became shorter in that process. Instead of W labels, all of them have W minus 1 labels. So this is an invitation to start a recursion. You can iterate this identity. You can now plug in to this term, well, precisely the thing which you did to the left-hand side. So also terms number 1, 2, and 3 are simpler in the sense that the weight is reduced by 1. The weight defined to be the number of labels in the polylog. And based on this simplification, we can start a recursion. So in principle, this tells you that you can always find such identities at the minor extent that the number of terms grows with each iteration step. But formally, we can treat the problem as solved as long as there's just one instance of CI labels. So let us just close the final gap. If there's not only one instance of Z within the labels, but several of them.
You still have an interval. The next stage you'll have a multiple interval. You have to compute it. But in terms 1 up to 3 are integrals, exactly. There's still a t.
Right.
So why have you reduced the weight? I mean, you're integrating something weight 1 vex, and then there's one integral, so it's the same way.
But integration is a harmless operation. I mean, if you go on with this procedure, then
you'll end up with just a single t.
Single t over there. A single t over there.
T, comma t. But with a whole bunch of stuff in front of
No, you end up with g, and no t before the semicolon, only t after the semicolon.
In the first terms, you haven't reduced the number of t's. I mean, the number
not
of
so
terms
far, but
with
I've
the
made a-
variable,
yeah.
you have still one occurrence of the final variable in the A level.
I do have, but I have
And
to
therefore, at the last
repeat.
stage, you'll be left with just g of t comma t.
This is where I disagree. No, you can always arrange that you are left with g0 comma t or g1 comma t.
One more application.
It will certainly work.
I don't know.
Maybe,
And then there's still the multiple integral then to do.
oh yeah, but then the integrals which are left over there are trivial in the sense that.
Just multi-z integrals. Let's move on.
Okay, I've wiped it out now, but the integrals which you are left with after sufficiently many steps of recursion, they are elementary. They can be carried out by just using the definition of the polylog. Yeah.
I'm sure it's true.
Okay, sorry
Can't
if
see it if
this,
it's-
sorry if this didn't become 100% transparent. Good, since time is pressing, let me make sure that I conclude. The last thing concerning the proof I wanted to say is, in case of more than just one instances of z in the label, then you get r copies of all the terms below this line. Remember, the first term is just from the partial derivative on the argument, whereas each partial derivative in a label generates 4 terms. So in that case, it's the same analysis goes through. You get r copies of terms 2 up to 5. And of course, the terms of this type, when you started with 2 instances of C, they will only have 1 instance of C. So you simplify in each step. Each term on the right-hand side will be simpler in whatsoever sense. Some of them in this sense that there's less C, and others are simpler in the sense that the weight is shorter. Yeah, so using this technology, you have obtained a recursive handle on the most complicated part of the Taylor expansion, namely if you have logs with the differences of 2 integration variables. So this nightmare case of the Taylor expansion is completely demystified using these recursive identities. Okay, so this concludes the main part of my talk, and ultimately it would be desirable to carry out this genus zero analysis also at higher genus, at the loops of string perturbation theory. Therefore, I want to leave a question to the audience. Do you think that we can proceed analogously to at higher genus? And in particular, I would be very happy to connect with the experts on elliptic polylogarithms or with the experts on those function systems, which might take the role of the polylogs for solving the scattering problem on a cylinder or some higher genus Riemann surface describing open strings. Yeah, looking forward to exciting conversations. Thank you very much for your attention.
Thanks very much. Yeah.
Yeah, I have a remark.
Yes.
Much as I dislike to say this, your method looks extremely similar, if not identical, to a special case of the method I used to prove the Goncharov-Manin conjecture in 2006, which calculates a more general family of integrals and proves that they're multiple Zeta values. I didn't use actual iterated integrals like this. I used elements in a bar construction. I used the symbol, which wasn't to be invented until 3 years later in 2009. And
Far-seeing.
sorry, yeah, that's funny, that isn't it? But actually, if it's of use to you, there are 3 implementations that I know of this in existence, which might be of some help. I have one which is not very good right here, Christian Bogner has recently finished one last year, and that will shortly be available for precisely this problem. And Eric Panzer has another implementation that's extremely close to this one, actually, in hyperlogs. And he uses this to compute 7-loop Feynman diagrams in quite core theory. But that also will be available very shortly. So you could apply his program immediately for this.
Almost all 7-loop Feynman diagrams, but not the one that I put question mark to on Monday. You will. This is another conference.
Okay, so I'm looking forward to look at the references you point out. Thank you. Okay.
So I heard, before your nice talk, two other nice things. I heard Stefan say that the multiple Zeta data mine had been quite useful to him, but I heard something much better than that from Francis, and that is that the multiple Zeta data mine is now massively overweight. It contains some information that is valuable and a lot that to him is trivial. So is there some project in your algorithmization to bypass the lookup tables that essentially you're using and use Francis's structure to get smarter?
Not in this particular context.
You just looked everything up.
So at the moment, our computer implementation includes the data mine process of reducing.
So you stopped at weight 21 because that's where your lookup table had stopped.
Essentially, yes.
Okay.
Bounced,
Well, Francis just saying to weight 21, he could write it on the back of a napkin.
No, wait,
Wasn't it weight 13? Wait. 13 on the back of the envelope, right?
Yeah.
He
Big
needs
envelope.
larger and larger envelopes.
Smaller and smaller writing.
Okay, no other questions? Well then, let's thank Oliver again.